Hi, this is Chuck. Welcome to the first of two videos on section 5.2, looking at the integration of growth and decay models. There will be two separate videos. The first one's primarily going to focus on future value, and the second one, present value. Let's start this off by first recalling what exponential growth looks like as a function. Recall that normally you have seen the formula P of t equals P sub 0 e to the RT, where P of t is the amount of whatever it is you might have, whether it be bacteria, a particular antibiotic in the bloodstream, or money invested in a mutual fund. At some point in time, P sub 0 is the initial amount, whether it be the initial count of bacteria, the initial quantity of antibiotic, or the initial funds that were invested. E to the R. R is the rate at which things are increasing or decreasing. Now, one of the things that you need to be very, very careful or mindful of is R must be the decimal, not percent, form of the increase or decrease. Okay, so if it's given to you as a percentage, you need to be careful to convert it back to a decimal before using it. In the formulas that we're going to be using today and in the next video, I'm going to follow the formatting that's used in the book. And in the book, instead of using e to the RT, they wind up using P sub 0 e to the KT. It's no big deal. So whether it be K or R, whichever form you're using of the equation, you need to be careful not to use the decimal form, or not to use the percent form, but to use the decimal form. Two formulas I want to take a look at. First one is if you have growth. Now, in a scenario where you have growth, to figure out what the total amount would be over a period of time, what you do is you integrate the E, and I'm going to start here using the KT dt. Okay, I can tell it's growth because the exponent on the E to the KT, this is a positive value. It's not a negative value. You'll see in a few minutes when we turn to decay that it's going to be a negative KT. We can actually integrate this fairly straightforwardly. Remembering P sub 0 is just a constant. So what we're going to get is that constant. And when you integrate e to the KT, you get back e to the KT and divide by the derivative of whatever this exponent was. The derivative is going to be K. We're going to evaluate from 0 to capital T. Now be careful, capital T is different from a lowercase t. Capital T represents a specific amount of time, for example, 5 years. Okay, so we go ahead and we evaluate this, and we're going to get P sub 0 over K e to the K capital T minus P sub 0 over K e to the K times 0. We can factor out the P sub 0 over K from each of those two terms, and what we'll be left with is e to the K capital T minus, now in the second case here, or in the second term, notice the exponent is 0. And whenever the exponent is a 0, that's the same thing as 1. So, a formula that we're going to be using for growth, okay, is this particular formula here. In the situation where we have decay, or in other words, things are going backwards or decreasing, a scenario where things would be decreasing would be the amount of antibiotic in the bloodstream. Okay, so the amount of it decreases over time, or if you take some represented very similarly. It's going to be the integral from 0 to capital T. We're going to have our p sub 0. And this time it's going to be e to the negative k lowercase t dt. The thing to be mindful of is with growth, you have a positive kt. With decay, you get the negative. If we integrate this, following a pattern similar to what we did last time, what we're going to get is our p sub 0. We're going to get it over. Now, when we take the derivative of this, it's going to be a negative k. And we're going to have our e to the negative kt. This being evaluated from 0 to capital T. This will then give us negative p sub 0 over k e to the negative k capital T minus a negative p sub 0 over k e to the negative k times 0. Things will behave similar to the previous example in some ways, with one very important difference. When we factor out the p sub 0 over k, as we did previously, this first term is going to be left with a negative. The second term is going to be the negative of a negative, so this is going to become a positive, and the sign will change. Now, let's look at this second term more carefully. After we have factored out the p sub 0 over k, and we have e to the negative k times 0, really e to the 0, that's going to leave us with a plus 1. Then, for this first or leading term here, we're going to wind up with a negative. Remember, we have factored out the p sub 0 over k, and that'll leave us with e to the negative kt, like that. Notice the two are reversed in order from one another, and in the case of decay, the exponent is a negative. Okay. So these two formulas are going to be important formulas. We're going to come back and use both of these as we go through both this first video and the second video. All right. In the book, they use k for this value for the rate of change because they want to be able to apply it to a variety of situations, not all economic or financial in nature. In most of the examples we're going to look at here, we're going to look at business and economic applications. So using the R would be appropriate as well. I will continue using K just in case you're following along in the book. All right, so first thing we're going to look at as far as economic business applications is something called future value. Future value isn't just something that will apply to business that may or may not be something you're headed into, but it applies to things that are going to apply to you personally as well. We'll talk about that. As far as computing future value, there are several different options. First one is if you have a single investment. So what this looks like is you take some money, you go to an investment firm or a business or wherever it is that you're going to invest this money. You walk in, you hand them the money, and you walk away. Okay. To do single investments, the value or the principal at any point in time is going to be the amount that you hand them originally, e to the kt. Now, this is assuming continuous compounding. Okay, this is not for quarterly or annual or anything like this. This means that you're constantly getting paid interest on whatever the balance is at that point in time. where it is compounded annually, that means at the end of each year, they look at how much money was there and they just at one point pay you the interest for the whole year. The advantage to continuous compounding is if you receive interest now, when they compute the interest moments from now, they will compute the interest not only what you gave them, but also the interest on the money that you were just given previously. So it allows for the interest to compound on top of what is already there. Let's take a look at a single investment. And let's say that you invest $36,500. Seems like an odd amount for right now, but it'll make sense here in a little bit. For 4 years at 3% compounded continuously. Because you're just at one point in time handing over a chunk of money, this $36,500, okay, and going to let it sit there for 4 years, we can use this formula that we have here. So the amount of money that you would have in 4 years is going to be equal to the amount you started with, 36,500, times e to the k. Now that's the rate at which it's growing. And remember, when we use this rate at which it's growing, we need to convert it back to a decimal. So it's going to be 0.03 times t is going to be 4 years. So the amount of money that you would have at the end of 4 years investing like this would be $41,153.64. Okay, so there's one way to look at investing. It's just a single investment, a one-time thing. You put the money there, you walk away, you come back some period of time later. A second way to invest, and this is more likely going to be the way that you're going to invest and save for retirement and things, is to invest in a continuous income stream. The idea of a continuous income stream is that there's always money being put in. Now, realistically, if, for example, you're saving for retirement, you're not going to be putting money in pennies, nickels, dimes, quarters every second of the day, 24 hours a day, 7 days a week. What it's really going to look like is every 2 weeks or every month, whenever you get paid, a portion of your paycheck is going to go into the retirement account. However, there is not a great deal of difference monetarily between computing a continuous compounding and computing an every 2 week compounding. Okay. Let's take a look at what's going on in this case. Let's say that you buy into a business, okay, and at the end of each year you receive, so at the end of each year, you receive $36,500, okay, for your investment from this business. So you're a part owner in some business, and you're part of the proceeds. Each year is $36,500. At the end of 4 years, how much money will you have? Well, this is an income stream where you receive your income annually or once a year. So what's going to happen is, if we continue with the same 3% rate of return, this is pretty low, but this would be something that you might put into a certificate of deposit or something like that, money that you're going to need to have available to you in maybe 4 years. Let's say that you're saving up money toward buying a house or buying something, and you want to be able to get at the money fairly easily, so you don't invest it in the stock market because that could go up, it could go down, and at the point when you want to be able invest it at 3%. Now remember, since this is the end of the first year and you're coming back in 4 years, you're only going to have this invested for 3 years. So this first year's investment, when you come back, is going to have grown to $39,900. The second year, you're going to receive another $36,500, which is the agreement on the contract when you bought into this company. You're going to invest it at 3%, but this time it's only going to be there for 2 years, so you're not going to get quite as much interest on it. And this will have grown to $38,757.03. The third year, you get the idea. You have the e to the 0.03 times, in this case, 1, and that's going to give you some amount. And then the fourth year, okay, remember you're receiving this money at the end of each year, and it's at the end of the fourth year that you're going to go back and say, hey, I need my money. So what will happen is, at the end of this fourth year, you're going to walk into the bank, you're going to have the $36,500 in your hand, but you're not going to invest it at all. So it's just going to be the $36,500. And when you add all 4 of these up, I didn't write this value down, you can figure that out for yourself. The total amount of money that you would have accumulated would be $152,805.98. So this would be the amount of money gained over this period of time by investing $36,500 each year. Now, the way this is set up, you only receive a payment one time a year, and that's at the very last day of the year. So on December 31st, somebody shows up and hands you a check for $36,500. Suppose this was set up to a slightly different situation. Suppose instead of receiving the $36,500 in one lump sum, every day you got paid the same amount. Well, if we took this $36,000 $36,500, and we divide it by 365 days, this would say that you would get $100 per day. Would you be better off receiving the $100 a day or receiving the lump sum $36,500 at the end of the year? Well, that depends. If you have to drive the money to the bank every day, you're going to be spending a lot of money, a lot of time and wear and tear on the car, running back and forth, and that may well exceed the amount of additional money gained in the way of interest. If the transfer can be made electronically, where it really isn't any effort on your part, you're better off going with $100 a day. Let's see how that would work. Okay, we could do this exact same thing as we set up here. Now, each year you're going to have made or received 365 payments. So what you're going to wind up with in the end is 4 years where every day there is some amount of money, $100, being deposited into this investment account that you have. So what this will look like is on day 1, at the end of the day, you're going to receive $100. You're going to invest this at 3%, and this is going to be in the bank or in the investment fund for 4 years minus the one day off of the 365 days of the 4th year. Okay, so remember, this wouldn't be exactly 4 years. It's going to be 1 day less than 4 years. And to get 1 day less, it's 1/365th, because there are 365 days in 1 year. Okay, so what this works out to be is a total of $112.60. this $100 that you put on at the end of the first business day will, at the end of 12 or 4 years, have grown to $112.74. On day 2, another deposit is made into your account for $100. It's still going to continue at this rate of 3%. And this time it's going to be in for 1 day less than the previous day. Okay? So we have to take away 2 days from that year. And what this works out to be is $112.73. You see, basically it's not a huge change, okay? But it is slightly less income than what we had before. If we continue all the way down to the last day, okay? So on the very last day of this 4-year term, at the end of the business day, they deposit $100 into the account, and at the end of that business day, you withdraw everything from the account. So this last $100 will not have had any time to sit there and accrue any interest. So what will happen is this will have been there for 4 years minus 4 years. In essence, it will have been there for no time at all, which means that you'll just have your $100. And the question then would be, gosh, what does this add up to? Well, I think you can see that in this situation, this is going to be a whole lot of deposits. It's going to be a total of 1,460 deposits. This would be a mess to figure out by hand. This can be written as the sum, because we're adding them up, where we start on the first day and we go up to the 1460th day. Now, how do I get 1460? Well, where this 1460 came from is 4 times 365. Yeah, I know that somewhere in there's a leap year, so there's a day missing, but we could work that in if we wanted to. And what's going to wind up being the case here is it's going to be $100 a day times whatever the interest is that is paid on that particular day's deposit. Well, this is going to be the 4 years minus how many days are we into the 4 years. Okay. So it could be written like that. Now, I'm going to do a little bit of changing here, which the reasoning for will become apparent as we move on. The 100 can be written as the 36,500 over 365. Okay? And I'm going to put down the delta t, change in time, is 1 over 365. Looks like it says and. Okay? The amount of change is 1 day for each deposit. So the change in time is going to be 1/365th of a year. Okay. With that in mind, we can rewrite this as the sum, where I goes from 1 to 1,460, still our 4 years. Now what I'm going to do here is I'm going to replace the 100 with this. So this is going to be 36,500 over 365, and we're going to have our e raised to the 0.03 times 4 minus I over 365. So we've not changed the exponent. The only thing we've done here is to change how we're writing 100. At the next step, I'm going to pull out part of this, and I'm going to take the 36,500 here's where things get a little bit on the interesting side. Up to this point, it's just been some algebra. What we're going to do is we're going to allow delta t to approach 0. In other words, suppose we were to take this and instead of getting a payment once a day, we got a payment once an hour of $4 and some odd cents. Or we got a payment every minute. Or we got a payment every second. By allowing delta t to go to 0, okay, we can rewrite this as 36,500. We've got our sum. T, okay, is going to be defined as 1 over, well, wait a minute. Our t is going to be the I over 365. Okay, so we can change this around. So we get t is equal to I over 365. Now notice this is the same I over 365 is up here. Okay, so we're going to change things around a little bit. And that'll allow us to rewrite some of this. What will allow us to rewrite this as, well, we got to do this. This is going to be 1460 over 365 because now we're dealing with t, which is in terms of years. So this goes up to 4. This is going to be written as e to the 0.03 times, we're going to have 4 minus t. Now we can say the 4 minus t because t is I over 365, which is exactly what we had up there. Where we're going with this is, as we allow t to approach 0 or to get really small, this then approximates an integral. Okay, remember we talked about how the partitions get smaller and smaller, so the change in x or the change in t gets smaller, and we can rewrite this as 36,500. Instead of summing up the individual parts, as t goes to 0 and you have an infinite number of parts, we're going to integrate from 0 to 4, e to the 0.03 times 4 minus t dt. Oops, got to explain that other stuff and I forgot the dt up here. Okay, now, do you have to remember all these steps? No. I'm not concerned about you remembering every single step in here. I do want you to understand, though, from this, if we start out saying, hey, let's break our payments down into smaller quantities and add up these smaller quantities. If we break them down into smaller quantities, it does make sense mathematically for this summation to eventually become an integral. Now, the good thing about an integral is you know how to do those. You can compute those. All right. So what we're going to do here now is some algebra. Seems like that's a whole lot of what we're doing. That's everything we've done up to this point except for converting from a sum to an integral. This can be rewritten as the integral from 0 to 4. Now, this can be e to the 0.03 times 4 minus 0.03 times t dt. All I did there was to take and to distribute the 0.03. Okay, if you have an exponent, like what we're looking at now, this can be broken up into separate parts. This can be broken up into e to the 0.12, which is really this, times e to the negative 0.03 t part of this is a number. The number can be factored out. And what we will have here is e to the 0.12 times this 36,500 integrated from 0 to 4, e to the negative 0.03t dt. At this point, I would be quite content with you just popping this into your calculator and then letting the calculator do the work. When you do that, using Math 9, you get $155,121.17. This is more than what we had before. If you take a look at the earlier computation, okay, when we go on up here we go. At this earlier stage, when we were just looking at investing at the end of each year, we wound up with $152,000. The difference between these two amounts, the $152,000 and $155,000, is the difference in the rate at which interest was compounding. In this case that we're looking at the top of the screen right now, there you only got interest once a year. Down here, we're assuming that there is money continuously going in, okay, and you could call daily close to continuously. Doesn't make a huge amount of difference, and it pays off an extra $3,000 or so. Okay. In this second case, we have an example of what is a continuous income stream. Okay. That means there's money constantly coming in. Realistically, for you, are you going to have a continuous income stream? Well, once you get some money invested and going in your retirement account, you'll be continuously receiving interest or valuation due to the stocks. Sometimes that's going to go down, though, just like it has here recently. Sometimes it will go up. But using this with a reasonable rate of return as an estimate, you can, in the long term, project how much a particular investment is going to be close to worth. Okay. All right. Let's do a definition here. This is going to be a future value continuous stream. What we're going to do here is we're going to pull together everything we've done. Okay, notice this is future value. Now it's real easy to tell if you want future value or present value. I've had people in past years ask, well, how do I know if it's a future value or present value? If the problem asks you, what is it worth now? Guess what that is? Is now in the present or is now in the future? If the problem asks you 5 years from now, what is it worth? Well, what's that going to be? Clearly, if they're asking for now, that's present value. If they're asking for a year, 5 years, 10 years down the road, that is a future value problem. And one of the things you're going to need to first identify on every problem that you're working on, homework, quizzes, tests, whatever, is whether you're doing a present or a future value, because they wind up using different equations. They're very similar, but they are different from one another. Okay. Definitions, two of them. Notice this is under the condition that you have a continuous stream. Okay. The amount that you will have at some point down the road is going to be the integral 0 to capital T r of t e to the k times capital T minus lowercase t dt, which simplifies to give you, and this is what we just did up here, okay, notice we have our e to the 0.03 times 0.4 out front. We have our e to the negative 0.03 times 4 inside. And hey, what's this 36,000? 36,500 outside, or if we wanted, it would be completely legit to move that right there. I left it out front because typically we factor constants out. But when I go to write this down here, and I put down what the formula looks like, e to the k capital T, the integral from 0 to capital T, r of t, e to the negative kt dt, I'm leaving this r of t inside. This r of t is the rate at which money is invested. We're going to see examples where the rate can be constant. We're going to see examples where it can vary. I'm leaving it inside of the integral right now because if this rate of investment has a variable in it, it's got to be left inside the integral. If it's just something like 36,500, it's fine leaving it outside. It won't hurt anything. Okay? This formula right here is an important one. I will provide that for you on quizzes and tests. Okay, that formula will be right there on the quiz or the test. You don't need to memorize it, but you do have to know how to use it. So be careful to make sure you work with this enough that you get comfortable knowing how to use it. Because if the formula is sitting right there, but you don't know what to do with it, it's not going to benefit you. Now, the scenario that we just worked above assumes that the rate of which money is being invested is constant, whether it be $100 a day or $36,500 a year. It was constant. We're going to do a specific case here. If R of t is a constant, for example, the $100 a day, the $36,500 a year, you can factor out it out, and the formula now can be written as e to the k, notice it's a capital T, r of t times the integral from 0 to capital T of e to the negative kt dt. But we've already done something like this earlier, and we can evaluate this integral just as we did way up there toward the start of things. And what this really works out to be is 1 over k and e to the negative kt. It's going to be a negative. So what we're going to wind up with, after you do some cleaning up of the formula and stuff, is a final form. I'm not going to go through all the details here. If you've got enough information to work them out yourself. But the final formula is going to be the rate of return, which is going to be a constant like 100 over k e to the k capital T minus 1. This formula is for a specific case. This only works when R of t is a constant. A constant means it's something like 100 or 36,500. Be careful, don't get them mixed up. You'll be given both of these on tests, quizzes, and things of that nature. Okay. But I won't provide any explanation as to which is used when. So you need to be working through your homework problems, aware of what you're using when, and keep things on track. Okay, so we've got these two formulas. They give you an example in the book. It's example 2. And the example they give you is a case where a surgeon is involved in some kind of an accident, and they're presently making $450,000 a year, which this amount, $225,000 per year for 20 years. Okay? If this person invests it, and this is kind of a waste of time, at 3.2%, but I'm sticking with that because that's what the book says, so we're going to follow along the example so that you've got something to check back in. Compounded continuously. Okay, so the idea this person is going to take the money, invest it, all the money that comes in each year, going to invest it for 20 years. And the question is, what is the future value? How much will they have? In 20 years. Clearly, this is future value because we're asking 20 years down the road. Now, one of the problems with this, it's okay just to look at it as an example, but if the surgeon isn't able to do surgery, they've lost their income and they're living off this $225,000 a year, which may sound a lot like us, but it depends on what your standard of living is. Okay, if they're living off of that, how are they going to have it to invest? Was the question I had in mind. But let's assume there's some other income that will provide for them to allow them to live day to day, and they're just going to take this $225,000 each year, put it into an investment, and then 20 years later come back and see what's there. Okay, question is, what is the future value? First thing you need to identify here is, what is the rate at which money is coming in? Well, it's a constant rate of $225,000. Okay. Notice this is a constant, so we can use the second equation that we just developed or were given up here in the definition earlier. The time frame that we're looking at is going to be 20 years. Now here's where you got to be careful. K, the rate of return, we're going to have to convert it back to a decimal, 0.032. Okay, so with that information, we can then compute what is the amount of money that's going to be in this account in 20 years. Well, if you take a look at the formula, it was R of T over K times E to the 0.0, well, let's just say KT for right now, minus 1. Where'd you get that, Chuck? That came from right here. Okay. We have a constant rate of cash flow. Okay, so with that, we can substitute in the information we have. R of T is 225,000. K is a 0.032. We're going to multiply this times E to the 0.032 times the 20 years, then subtract 1. Now be careful how you enter this into your calculator. You want to start with that portion which is within the brackets first. First put in your calculator E to the 0.032 times 20 equals, get a number, subtract 1. Then you can multiply that times the 225,000 equals, get a number, then divide by the 0.032, and when you do that, the value that you wind up with is approximately, within a few pennies, $6,303,381. And you say, wow, that's a lot of money. And it is a good chunk of money. But think about the fact that that's only half what they were originally making. So they've actually wound up losing a good chunk of money. Yes, they don't have to go to work every day. But I doubt that they would take the 12 years to train to be a surgeon to just want to sit home on the couch. there is an example of a situation where you have a constant rate of income. Let's take a look at a different one. This one isn't in a book. Let's say you get a job, a career job, what you're training for, okay? And you remember back to having taken this particular course, and you think, oh yeah, I need to start saving toward retirement. If you start saving early, you will have a considerable chunk of money by the time you retire, and you'll be in great shape. In fact, one of the neat things is you'll be able to decide when you retire, because you won't have to wait for some amount of money or people to tell you, yeah, you've worked enough years, you can retire. Once you get enough money, if you're done working, you retire. Okay, let's say the company matches your retirement investment. Now, they do not match limitlessly. It's usually like 2, 3, 5% of whatever it is you invest. Okay. Giving you a total between what you put in and what the company puts in, let's say of $8,000 a year. This is not a huge amount of money. Okay. If they're investing in this as well as you, that's about $700 a month, less than $700 a month, and only half of that is what you've put in, so that's $350 a month, which is not going to be a huge amount out of your paycheck once you get a career salary going. Okay, give me a total of $8,000 a year. The stock market usually goes 10 or 11%. Let's do this a bit conservatively so that you will probably wind up with more money than what this example will suggest. But winding up with more than what you thought you were going to have is a good thing. Okay. In this case, you're not just taking and depositing the money once a year. It's being put in every week, every 2 weeks, every however often it is that your company pays you. So what we're going to do is treat this in two different ways. First, we're going to look at how much would it be if you just did it once a year. Okay? So the first way we're going to compute this is as once a year. Because that's pretty straightforward to do. And let's say once a year you're going to drop in this $8,000. And let's say you work for 35 years. Okay? So if you were to drop it in once a year, this is actually going to be lower than what would actually come out. Okay? Because remember, that money's just sitting there, I don't know, in a coffee can in your backyard till the end of the year, and you drop the $8,000 in. So you got money sitting there doing nothing for an entire year before it's invested. And that's not what's really going to happen. But this is the most conservative scenario. In 35 years, what this will work out to be is the rate at which the money's coming in divided by the rate of return times E raised to the rate at which the money's coming in times the 35 years that you would estimate you're going to work minus 1. Carefully plug that into the calculator, and this estimate would suggest that you're going to have $1,985,427.96. That's not bad, about $2 million. Now remember, this is a low estimate in two ways. Low in that the stock market usually returns 10 or 11%, so the rate of return that we've put in is lower than expected. Second, it's going to be low because it's assuming that you're letting your money sit in a coffee can somewhere till the end of the year instead of being invested and earning money. Okay? is if you deposit once a year. Okay. Now there's another problem with this too. And that problem is, this is somebody that's, I mean, if this is describing your 35-year career, you've not done very well at all. You may be sitting there thinking, you got to be kidding. I got $2 million saved up. Yeah, well, that's not very good, because what this is assuming is, over your entire career, every year you've put in $8,000. That means for 35 years you never got a raise. Really? Okay, that doesn't sound so great to me. Because if you get raises, you can increase the amount that you deposit in the investment. Okay. Let's change this a little bit. Let's go with a second scenario here. Let's say that on average you get a 2% raise a year. Okay? And if you get a 2% raise, that means that you can increase by 2% the amount of money that you're putting into the retirement account each year. Okay. Now, what does the rate of investment look like there? Well, what it's going to look like in this case is you're going to have R of T is going to be the $8,000 that you put in the first year times, we're going to increase this by 2% every year. Okay, so this is going to allow for growth each year. And in this case now, notice that the rate of investment changes every year. It has a variable T in it. Right there it is, which means that we can no longer use this formula that we've been working with, this second one, because this second formula assumes R is constant. Well, it's no longer constant. How are we going to deal with this? Aha! We're going to have to use the first formula within the definition of future value, which is the e to the kt with this integral. Alright, so let's go back, make this a little bit more realistic. Let's assume that you're actually getting raises. The amount of money that you'll have at the end of that same period of time is computed by e to the k, capital T, the integral from 0 to capital T, R of T, e to the negative k, lowercase t, dt. That you'll be given on the test, quiz, final exam, whatever it is. Okay. The catch is, well, I've got it, what do I do with it? Okay, so let's start plugging things in. We're going to have E. K is the interest rate, 0.095. Capital T is how many years you plan on working, 35. The integral is going to go from 0 to capital T, 35. The rate at which money is coming in is now going to be this 8,000 times 1.02 to the T times e to the negative 0.09 t dt. This is something that you could do by hand. Really? That might take a little work. It would. An easier way to do this is to plug it into your calculator. If you have a calculator, let's see, need a bracket there, where when you go to Math 9 it gives you the integral with the little boxes. Okay. It's easy enough to fill in the boxes appropriately. Be careful when you put this into the calculator that all of this is within a set of brackets. Okay, so that you can set things off. Now, what this would look like in your calculator would be parentheses 8,000 times 1.02 raised to the x parentheses. Then you're going to have your e, and you're going to have your that this is also in parentheses. This, with the parentheses, the way I have it written out here is if you have one of the calculators that displays it in the form FNINT, which is what my calculator does, the way I would do this would be 8,000 times 1.02 raised to the x, close the parentheses, times e raised to parentheses, and we're going to have our 0.09x, close the parentheses. I'm going to get rid of this for right now. Okay, so we've got all of our parentheses closed. Put in x, put in 0, put in 35, press enter. Now you got to be really careful. You got to be really careful. People forget about this because we still have this 0.09 times 35, and this is going to be times whatever the result is from this. So it's going to give you some number, and the number that you should get is 104,197.69. When you multiply that all out, you should come up with $2,431,563.94. Now recall that the first example I mentioned to you was going to be low because it's assuming you're just putting the money in once a year and you never get a raise. This is assuming a 2% a year, and it's assuming that you're putting it in every couple of weeks. The difference is about $500,000. Okay, you go from 1.9 million to 2.4 million. That's about an extra $500,000